Welcome back. So, all right, now we're on to more complicated things where we have some, piecewise functions. So I've kind of said a couple times, just offhand, that Laplace transforms can be like really good for solving differential equations where like you have some piecewise functions showing up in there. So, something like this where you have your function can be given by different formulas on different pieces of your domain. So we have kind of seen before that like you could just like directly like compute all of these things, just using like the definition and then like actually doing the integral and stuff like that. But it'd be great to avoid doing all those integrals and just sort of have some formulas and standard things that we can do to just shorten our process. And so the thing that's going to do that for us is called the unit step function. So for each constant a, which is going to be specifically positive for our purposes, the unit step function is given by either 0 or 1. And it's 0 if your input t is between 0 and a, strictly less than a, and it is equal to 1 if t is greater than or equal to a. All right, so what does this thing kind of look like? So it looks something like this. So you have like a, so it's just going to be 0 from here up until you get to whatever your value of a is, and then it just jumps up to 1 at that point. Okay, so this is your unit step function. By the way, the textbook denotes this as u of t minus a, so they have like just u of t is like just equal to 0 or 1, where this is like when t is less than or equal to 0, and this is when t is greater than or equal to 0. I think this was supposed to be strictly less than. And so you can like just say u sub a of t is like a translation by like a units, and I don't know, I think that's kind of weird, so we're just gonna do this. This is like a little bit more intuitive. It's not gonna really change anything to just use slightly different notation. All right, so how can we write a function, some piecewise function like this, nicely using the unit step function? So that's like the whole point of unit step function, is that we can take piecewise functions and write them nicely using this thing. All right, so how we would do that is we take this piecewise function and we could just say, all right, well, start with just alpha of t and then add it to u sub a of t times beta of t minus alpha of t. So this is going to look really weird, but it turns out that this is just a nice formula for this piecewise function f of t. And how do we check that? Well, if t is less than a, so, or I should probably say 0 is less than t less than a, doesn't really matter. Then alpha of t plus ua of t beta of t minus alpha of t. What is this equal to? Well, this would just be 0. So this whole thing would just go away, and we're just left with alpha of t. Okay. And if t is going to be bigger than a, so we'll be on this piece, then what do we get? What would this be equal to? Well, this is now going to be equal to 1. So we get alpha of t plus 1 times beta of t minus alpha of t. And so, of course, this alpha of t and this negative alpha of t are just going to cancel, and we're left with beta of t. So, to summarize, if t is between 0 and a, then this formula just gives us alpha of t. We get that. And if t is greater than a, then this formula gives us beta of t. So this can just be rewritten more simply without any cases as just this combination of functions. So the second translation theorem is, well, what if we want to just have f of t times our unit step function and take the Laplace transform of that? What does that look like? So this looks pretty weird, so I'm referring to my notes here because I do not have this one memorized. So this is equal to e to the negative as times Laplace transform of f of t plus a of s. Okay, so instead of the Laplace transform of f of t, we have the Laplace transform of f of t plus a, but we're also multiplying by this e to the negative as on the outside. All right, an alternative form that you might see this written as sometimes would be e to the, if you're using the u of t minus a, like the book's notation, you might see this written as e to the negative as times L of f of t of s. But notice that over here, instead of an f of t, you have an f of t minus a. These formulas are effectively doing the same thing for you. As long as you just apply them and correctly, they'll both do the same exact thing for you. All right, so where the heck is this coming from? So let's just do, we won't do the alternative form, we'll just do this guy. This guy is equal to, by definition, 0 to infinity, e to the negative st times f of t u alpha of t dt. So this is either equal to 0 or 1, depending on if we are, depending on if t is bigger or less than a. So let's split this integral up into the integral from 0 to a plus the integral from a to infinity. Okay, so we'll just split this integral up like so, and we'll just copy paste this guy into here and then to here, with the exception being that from 0 to a, the unit step function is just equal to 0, which is equal to 0 from 0 to a, then it's equal to 1 from there on after. So this is equal to e to the negative st times f of t times 0 dt from 0 to a, and then from a to infinity, it's equal to e to the negative st times f of t times 1 dt. I don't really need to write that 1. Really, this whole thing's just equal to 0 anyway. So I get a to infinity, e to the negative st, f of t dt. And now I'm going to do a translation. So I'm going to replace t with t minus a. So instead of e to the negative st, I'll have t, sorry, no, not minus a, plus a. and then f of t plus a. All right, why the heck am I doing that? Well, because I'm trying to change these bounds over here. So instead of having bounds from a to infinity, it would be good to have bounds from 0 to infinity. But that's not going to happen if we're using t, because t starts at a and ends at infinity, right? But t plus a, if t starts at a, wait a second. Wait a second. I think this is fine. Yeah, this is, okay, so this is from t equals a to infinity. Okay. Yeah, okay, yeah, I just said it wrong. So over here, t is going from 0 to infinity. Over here, t is going from a to infinity. But we're plugging in, if we start by plugging in t equals a, then over here I get like negative s times a. Over here, if I start by plugging in t equals 0, then I still get negative s times a, because I'm getting like negative s times like 0 plus a. Okay, so these start by, over here, t starts at a, over here, t starts at 0, but this thing and this thing really start at, if t is 0 over here, then they're starting at a over here, and they're starting at a over here, and then they're going to infinity for both of them. So these integrals are the same thing. I'm just tripping myself up. All right. Anyway, this now, this negative s times t plus a, I can rewrite that as e to the negative sa times e to the negative st times f of t dt. And this right here, I could just pull it out of the integral, and I'm left with e to the negative sa times this whole integral. But what is that whole integral equal to? Is just the Laplace transform of f of, oh, I forgot to write t plus a. This is just the Laplace transform of t plus a. Of s, whatever. All right. And this now finally is the same thing that we have up here. All right. Anyway, so kind of butchered that a little bit, but this is not my first take, so I'm just going to kind of leave that one. All right. Laplace transform of t squared times u3 of t. What is that equal to? All right, so function times u a of t. So we multiply by e to the negative as. A is 3, so negative 3 times s. And then times the Laplace transform of, okay, so f of t, this is like, this t squared is our f of t. And yeah, so this would be not t squared, but t plus a squared. So we would get that. All right. So this is e to the negative 3s times the Laplace transform of t squared plus 6t plus 9, which is equal to e to the negative 3s times, parentheses, the Laplace transform of t squared, which is 2 over s cubed, plus 6 times the Laplace transform of t, which is 6 over, which is 1 over s squared, plus the Laplace transform of just 1 is just 1 over s, so for 9 it's just 9 over s. So we should get something like this. And let me just check my answer, make sure that I'm getting the right thing. Yeah, all right, good. Cool. And then for cosine of t minus pi times u sub pi of t, what should we get? All right. So I would recommend at this point just pausing the video and trying to do this one on your own, and just taking a breath and taking in all of the stuff that we've discussed so far. So try this one, pause, pause, and then unpause, and then we'll do it together. All right. So I'm just gonna go ahead. All right. So applying this formula. By multiplying by u sub pi of t, this would be equal to e to the negative as times the Laplace transform of f of t plus a. Our f is just like cosine of t minus pi. So it would be cosine of, now instead of t, we're going to write t plus a, so it would be like t plus pi, and then there's still the minus pi from before. So this is e to the negative pi s times the Laplace transform of just cosine of t. And cosine of t just gives us s over s squared plus 1 squared. So this should be our Laplace transform. All right, we can invert this too. So the inverse Laplace transform of e to the negative as times L of g of t of s is equal to g of t minus a u a of t. All right, so what you should take away from this is that we're really just taking this same exact formula and just writing it backwards. This formula is like kind of complicated in my opinion. I have a tough time wrapping my head around it sometimes. As you can obviously tell. But yeah, so the inverse Laplace transform, we're really just sort of reversing all the roles, everything here. I don't know why we decided to go with G's instead of F's here, but it's all the same. Yeah, you could rewrite this slightly. So like G of S is equal to, capital G of S is just the Laplace transform of G of t s. And so you could write this as like L inverse of e to the negative s as times just capital G of s is equal to G of t minus a u a of t. So you can just do that. But let's see how to do this in an example. So L inverse of e to the negative 3s times 1 over s times s plus 1. All right, so here we have e to the negative as times something, right? So what's going on here? This is like taking the place of our g of s. So this is equal to g of little g of t minus a. And what is a? So a is 3 here. So this is t minus a, so t minus 3 times u 3 of t. So that's just what this is equal to. And now what we need to figure out is what this little g is. And what is little g? So if we figure out little g of t, then we'll be done. So little g of t is just the inverse Laplace of 1 over s times s plus 1. And this is, all right, well, let's do the partial fractions thing again. So 1 over s plus 1 is equal to something over s plus something over s plus 1. Let's see, if I make this a 1 and that a negative 1, I think this will work out, because then up here I'll get s plus 1, and then over here I'll get negative s after like finding a common denominator and adding all this stuff together, which would leave us with just 1, so I think this works. So this is L inverse of, I'm supposed to use square brackets, whatever, 1 over s plus L inverse of negative 1 over s plus 1. And this is t minus e to the negative t, if I apply those formulas correctly. Yeah, wait. Oh, no. This should just be 1. Sorry, if it was t, then that would give me like 1 over s squared. 1 gives me 1 over s. All right, so inverse Laplace of 1 over s is just 1. Inverse Laplace of 1 over s plus 1 is e to the negative t. All right, so this is little g of t. So then g of t minus 3, returning to our problem at hand, is 1 minus e to the negative t minus 3. Boom. All right. So yeah, that's how we do that one. And so to put it all together, let's solve this differential equation right here. There's this initial value problem. We have y double prime plus y equals t minus 3 times u sub 3. And we have y of 0 equals 0, y prime of 0 equals 1. So we'll do the Laplace transform of the round brackets, y double prime plus y is equal to the Laplace transform of the right-hand side. We're going to need to know the Laplace transform of y double prime, so let's refer to formulas. So the Laplace transform of y double prime is equal to s squared y of s minus y of 0s minus y prime of 0. Just put that over here. I guess I probably could have put it over here. So I get this on the left-hand side, plus the Laplace transform of just y, which is, by definition, just capital Y of s. And then the right-hand side, what's the Laplace transform of t minus 3 times u sub 3? All right. So apply this second translation theorem. So f of t times u sub 3. This is our f of t. This is our u sub 3. So a is 3. So a is 3, so it's going to be e to the negative 3s times something. It's going to be like L of something. And this times L of f of t plus a. So a is 3, so it's f of t plus 3. So replace t with t plus 3. So we replace all instances of t in our f with just t plus 3. And then this will conveniently cancel out to just a t. So we just do the Laplace transform of t, which is equal to 1 over s squared. All right, let's deal with the left-hand side now. Just going to copy that because we're not doing anything there. All right, y of 0 is 0. Y prime of 0 is 1. So this is 0. This is 1. So this thing goes away. And this is just a minus 1. So we get, and we could factor out a capital Y of s from this term and this term. So we get s squared minus, or s squared plus 1 times y of s, and then minus 1 from there equals this. Now let's solve for y of s. we divide by s squared plus 1. This would be just plus 1 over s squared plus 1. And now we're almost done. We just need to take Laplace transform, or the inverse Laplace transform. So little y of t is just L inverse of y of s, which is just L inverse of our right-hand side. All right, so we just have to deal with this. All right. So this is our last example. So again, I think probably I would recommend pausing the video here and then attempting to find L inverse of the right-hand side, just applying all of the formulas that we've kind of discussed so far. And if you're able to take L inverse of this right-hand side, then you're probably doing pretty good so far. All right, so I'm just gonna kind of go ahead and try to do it. Okay, before I do, I'm going to do partial fractions on this. So 1 over s squared plus 1. I'm going to write that as as plus b over s squared plus cs plus d over s squared plus 1. All right, so finding common denominators and stuff, I'll get as plus b times s squared plus 1 plus cs plus d times s squared. So that's cs cubed plus ds squared. That should equal 1. So we get as cubed plus b s squared plus as plus b. That all comes along. All right, s cubed terms, s squared terms, s terms, and constant terms. So we get some equations. We should get the s cubed terms. There aren't any s cubed terms on the left side of the equation, so I could just say my a plus c is equal to 0. All right, the s squared terms tell me that b plus d is equal to 0. The s terms, there are no s terms on the left side, so that just tells me a is equal to 0, which conveniently tells me that c is also 0. And b is just equal to 1. That one's just free. So b plus d equals 0 tells me d equals -1. All right, so now let's take this partial fraction decomposition and throw it up here. All right, so a and c are both 0, so those just go away. So we get b over s squared plus d over s squared plus 1. So b is 1, so we just get 1 over s squared plus L inverse of e to the -3s times d is -1 over s squared plus 1. And I'm just going to make this term over here, just make that negative. And then plus L inverse of 1 over s squared plus 1. All right. Let's just take this and then just go down to the next page. All right. 1 over s squared plus 1. That one should be easy, so let's deal with this one first. It looks like this, so this is just going to be sine of t. And these ones will be the slightly harder ones. All right, so e to the -3s times something. We're taking L inverse of e to the -3s times something. So we do L inverse of e to the negative 3s times something. Bring this down here too. All right, so this would be our, this and this are going to be like our g of s. All right, so if capital G of s is equal to 1 over s squared, then what would g of t be? Be L inverse of g of s, or L inverse of 1 over s squared. What's L inverse of 1 over s squared? What gives me 1 over s squared? Just go over here. Well, it'll just be t. So the Laplace transform of t is 1 over s squared. So that would be my g of t for this guy. What would my g of t be, my little g of t be for this guy? Well, if capital G of s is equal to 1 over s squared plus 1, then little g of t is equal to L inverse of 1 over s squared plus 1. And what is that equal to? What gives me s squared plus 1? Oh, well, we just did that. Just sine of t. Okay. So now we can apply this formula to this and this. So y of t equals, all right, so a is 3 in this case, right? So we're going to get g of t minus 3. So for this one, instead of t, we'll have t minus 3, and then times u sub 3 of t. And then, minus this thing. This will be sine of not t, but t minus a, or t minus 3, times u sub 3 of t, and then plus sine of t from the last term. All right, and let me check with what I had before. T minus 3, u sub 3, sine of t minus 3, u3, and sine of t. Okay, so yeah, this is what I had before, so I'm pretty confident in this answer at this point. And yeah, so that's how you do it. A lot of formulas, a lot of moving parts in these things. It's definitely complicated, but it lets you, solve, we're solving progressively like more and more complicated differential equations, so it's to be expected. But yeah, so that's how you do it. Thank you for being patient with me and doing this asynchronous week. I will be back in a couple weeks. On what day am I going to be back? I don't even know what today is.